awkward, but okay. This particular video will have to do with t-test, which is the basic, simple way of looking at differences between groups. And first, we have to kind of make sure that you understand that most of statistics is related to dealing with differences between group means. Now, sometimes it's differences between two different groups, like a sample and an experimental group, experimental and a control group, or different dosages and the response to different dosages, or things like how does performance in a group really stack up against performance in a kind of a benchmark, sort of a national benchmark or a state benchmark or a larger population standard. And so we're always talking about means. And in general, statistics deals with means. It doesn't necessarily deal with individual cases, because we know that there are fairly big differences between what we know about groups and what we know about individuals because of that normal distribution idea. And so back in the previous video, I kind of dealt with this notion of looking at what we called a standard normal distribution. And this standard normal distribution is created by converting raw numbers, raw scores, into what are called standard scores, or in terms of the statistic, what is called z-scores. And a z-score is defined by a raw score, an individual score, minus the mean of that group, divided by this thing that's called standard deviation. Now, it's not really important to know, how those things kind of all come together and how they're calculated, and it's not really important to know that. What is important to know is that what's actually happening is on the top of this ratio is some sort of comparative quantity. Could be a difference. In this case, it's a difference between a score and a mean of the group that score comes from. And on the bottom is what we refer to as an error term, or what is sometimes called an unbiased estimate of error. And that unbiased estimate of error is really a way in which we figure out what would random error look like. What would random error look like? And another way of thinking about this is that on the bottom of this, on the top of this thing, is what we might be called the observed error. In other words, the difference between you know, a mean and or two means or whatever. And what's really on the bottom of it then is once again random error. And so it's always this idea that we're making comparisons between what we'd expect purely by chance. What would we expect if there were nothing going on? And that's the random error, and what we have actually observed in terms of difference between groups or difference between an individual and a group. Yeah. Z-scores make it kind of easy. And we always, when we look at these different distributions, and not all of them will look like normal distributions, some of them will look different because they only become normal. All these distributions become normal when we have an infinite number of cases in the set or an infinite number of numbers in the group. And so that's the only point at which we can truly count on all these distributions being normal, is when they're at infinity. Well, we're not at infinity in anything that we might do. In fact, it would be an absurdity to say that we're operating at infinity. And so that's why we call these things as unbiased estimates of error, because we really don't know. We're just taking our best shot at using you know, mathematical processes to develop this notion of unbiased estimate of error. The way this practically works, let me get another color here so you can see this, is that on this standard normal distribution, the mean is in the middle, and this is that's supposed to be a funky M. And the value, the z-score value there is 0. So it's 0 in the middle. We go up 1 standard deviation unit. So this is +1 standard deviation unit. We go up 2, +2. And by the time we get to +3, we're almost, the two lines are almost together. Well, this is a symmetrical distribution. So if we come down 1 standard deviation unit, that's a -1 z-score, or a minus or 1 standard deviation unit down. And if we come down 2, that's a z-score of -2 or 2 standard deviation units down. Now, as it turns out, this standard normal distribution is highly predictable, highly predictable. And so this midpoint, this 0 z-score, is what we would call the 50th percentile. Now, I'm going to use a percent sign, just kind of shorthand here. It's not really percent. It's not really a percentage. Percentile is talking about the amount of surface underneath the curve. And so at the 50th percentile, exactly 50% of the surface lies below there and 50% lies above there. And we always know that roughly 34% of the surface lies in the first standard deviation unit, and roughly 13.5% of the surface or space lies between the first and second standard deviation unit. So this becomes -13.5. And for all practical purposes, that's really all we need to know about the surface area under this curve. Because if you accept this to be the 50th percentile, then if we add another 34% of the area to that, this becomes the 84th percentile. You add another 13.5% surface to that, this becomes the 97.5 percentile. And it works the other way, except it subtracts. And so the 50th percentile minus 34% of the space is 16th percentile. And minus 2 standard deviation units is 16.5, or excuse me, 16th percentile minus another 13.5% of the space. And so this becomes the roughly 2.5 percentile. Now, some things to notice about the standard normal distribution is that, like all standard distributions, all normal distributions, most of the area is in the center. And so most of the cases occur near the center. And if you think about things in life, most of the things that we might measure about individuals, we find that we're most like each other as opposed to unlike each other. And so if I'm measuring height, almost everybody is about the same height, you know, a large percentage are relatively in the same height range. And as people get taller and taller and taller, there are fewer and fewer and fewer people as people get less height enhanced. On the other direction, there are fewer and fewer people. So there are not a lot of people 4 foot tall, and there are not a lot of guys, you know, 7'6". But there are an awful lot of guys in that mid-range. And so that's what we know about this distribution. And in fact, you know, I grew up back in the day when multimedia meant that you had different colored chalks. And so now I have different colored pens as my multimedia device. So what happens is that if you look at the difference between -2 and +2 standard deviation units, that encompasses, makes a real messy graphic, but that encompasses 95% of the space. Now, it's not exact. I've rounded these percentages off just a little, but it's pretty close. And so if we observe something that occurs in this middle 95%, if we observe something that occurs within this 95%, we would say in that area, that happened by random chance. And that's random error. And if something's out here in either this 2.5% or this 2.5%, we say that's the area of 5% systemic error. And so if we observe something in this area of systemic error, we say that is a significant outcome. And if something is up here as opposed to that, in the 95% area, we say that is not significant. And that's in a nutshell about 90% of the logic that's used in simple linear statistics. We're always making an estimate of what we would expect to see purely by chance, if nothing were going on. And we're comparing what we observe to that estimate. And it's generating a statistic. And let's do an example or two here. I'm out of color, so I'm going to have to fall back into some basic stuff. This will go up on the As You Learn site too. This particular, these doodles all end up there. Let's talk about a particular scenario. Let's say we gave an exam, and for that exam, the average score for the exam was 79. And the standard deviation for that exam was 5. Now, if a student made, let's say student A had a score of 66, and student B had a score of 86. That would mean that student A's z-score value or standard score value would be 66 minus 79 divided by 5. And student B's z-score value would be 86 minus 79 divided by 5. Find a better pen here. Okay. And so what does this turn out to be? This turns out to be minus 13 divided by 5 is minus 2.6. Minus 2.6 z-score. And the 86 compared to 79 divided by 5 ends up being 7 divided by 5, right? 7 divided by 5. And so this ends up being a positive 1.4. I hope. I can still do simple math. So student A with a score, z-score of minus 2.6 is going to be out here somewhere. A's out there, say about right there. And student B with a positive 1.4 is going to be here. So student A scored significantly different on this exam than did the class. In fact, they scored significantly lower than the class. Now, the difference there, significantly different, is what's called a two-tailed response. Doesn't matter, it could be at one end or the other. And significantly lower means the directionality is important, that student scored lower. And not only lower, but significantly lower. Student B, on the other hand, with a value of 1.4, scored within the range of random error for the class. And so their score is not significantly different than the rest of the class. Any questions about any of that, any of this whole page full of scribbles?
Sir, can you hear me?
Yes, I can hear you.
Okay, this is Deborah. I'm driving home from work, so I finally figured out how to get this on the phone. But I thought I heard you say something about two tails. Could you explain that again, please?
Sure. Yeah. Let me. Well, let's talk about up here. Okay. In fact, I don't want to cluster it up all that much more. I'm going to take this page off for a minute and use another page, simply because it's easier to see this when you're working with a clean page. You'd think after 45 years I'd be good at drawing this stuff, but I'm not really. I'm still in my stick figure stage, so I don't know how art literature got together. But this is the mean value, and this is 0, z-scores. Go up 1, plus 1, go up plus 2, down minus 1, down minus 2. Now, the area, the space in between plus 2 and minus 2 represents 95% of the space. Now, This is a two-tailed, because the error could be, we don't really care whether it's in the 2.5% that's at the top or the 2.5% that's at the bottom. If it occurs in either one of those two places, if the value is in either one of these two places, we say it's significantly different.
Right.
Now, let's say direction matters. Direction matters. And we're wanting to know which students score lower, significantly lower.
Okay.
We could take that 95% and push it all the way down to the boundary here, or excuse me, I'm the other way around. If, let's say we were asked the question, did a student score higher, significantly higher? The bottom 95% then becomes the random error piece, because I could care less if it scores how many standard deviations lower, because I'm only worried if it is up in the 5% that's higher. And so the green line here represents a two-tailed question. The red line represents a one-tailed question. And so the value of the point, which is the critical value, changes.
Okay.
Because I want it to be at the point where 5 percentile is above that, then that becomes critical value. Now, if you go to the other end of the scale and say, okay, well, let's do we want to know who's lower. So we take the 95% that's at the top of the distribution, that becomes our random error. And then the 5% that's down at the bottom of the distribution becomes our area of significance.
Okay.
So for the, for the two-tailed test, it doesn't matter whether it's out here or out here. For the one-tailed test in a positive direction, it's got to be out here someplace. And for the one-tailed test in a negative direction, it's got to be out here someplace.
Okay.
Now.
So it has to be, if it's going to be for a one-tailed test going in the positive direction, it has to be
above the 95th percentile. Yeah.
Above the 95th percentile. Okay.
Essentially, yeah. And if it's in a negative direction, it's got to be below the 5th percentile.
Okay, I understand now. Thank you.
Now, you might notice here that values that are significant for a one-tailed test can be not significant for a two-tailed test. It takes a lower z-score value to be significant for a one-tailed test at the high side, and a higher z-score value can still be significant on a one-tailed test at the low side. And so the difference doesn't have to be as great between whatever we're comparing for it to be significant if we're looking at a one-tailed test. And that's why I always encourage researchers and dissertation students and folks like that, ask one-tailed questions. Your statistics are more powerful on one-tailed questions simply because the difference doesn't have to be as great, but it's got to be in the right direction.
So if you wanted to ask a one-tailed question versus a two-tailed question, how would you phrase it differently?
Yeah, I might say, let's say we're looking at two groups, or no, this is still individual scores. So let's say I want to know which students in the class scored significantly different than the rest of the class.
Okay, and that could be,
high or low, it doesn't matter.
Okay.
Could be either.
And that's what would make it a two-tailed test, because it could be higher or lower. You didn't specify.
No, I didn't specify which direction.
Okay.
If I say, I want to know, I'm really worried about the students that are not scoring as well. How many students, which students scored significantly lower than the rest of the class? Then that becomes a one-tailed on
the left side.
Yeah.
Okay.
Or conversely, I want to know which students scored significantly higher, then it becomes one-tailed on the high side.
Okay, thank you.
But it can make a difference in significance sometimes if it's if it's in a gray area, it can make a difference.
Okay.
So are we okay with the logic right now?
Yes, sir. That helped me a lot.
Anyone else before I'm going to make a big jump here now. If you go back and you remember all that's the really compelling stuff that was in that little cartoon video of rabbits and dragons. There were two really main ideas in there. One had to do with this notion of when you have randomly occurring events, they will be normally distributed. But very often you can't get enough sample, you can't get enough replication to really get to the point where it begins to look normal, perhaps. I mean, you have to have more and more and more to figure out, what the distribution looks like and that it is normal. However, if you begin to look at samples, random samples, the random sample means are normally distributed. And for that, I'm going to take a simple little example just to kind of show that it's the simplest little example in the world. I used to, just for the heck of it, call it the Gilligan's Island example. And, in the first song, first theme song of Gilligan's Island, the first year, there were only 5 people in the song because we were all expecting, they were expecting that to be the cast. And then when they did their, all their focus group stuff and all like that, they figured out, well, wait a minute, we need something else here. We need, more dynamic here. We got to have more interaction. So they added 2 more characters, and the 2 characters that are added were the Professor and Mary Ann. And so what happened in the process was when they added the Professor and Mary Ann, the second year of the show, the song had 7 names in it, not 5. But the first year it only had 5. So let's say it was, we took some score on these folks for the 5 people during the first year. And those scores were 3, 4, 5, 6, and 7. So each one of those scores represents some character in the show, except Professor and Mary Ann, who were second year. And so if that's the entire population in Gilligan's Island, so this is the population, of Gilligan's Island. If we were to take all possible samples size 2, that would be 10 samples. And let me do those real quick. So it's, the samples are, one is 3 and 4, one is 3 and 5, 3 and 6, 3 and 7, 4 and 5, 4 and 6, 4 and 7, 5 and 6, 5 and 7, and 6 and 7. Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. There are no other possible samples size 2. Those are all the unique possible samples. No other samples. Now, if we took the mean of each of these, the mean of 3 and 4 would be 3.5. The mean of 3 and 5 would be 4. The mean of 3 and 6 would be 4.5. The mean of 3 and 7 would be 5. The mean of 4 and 5, that's 9, would be 4.5. The mean of 4 and 6, 10, would be 5. The mean of 4 and 7, 11, would be 5.5. The mean of 5 and 6 would be 11, so that would be 5.5. 5 and 7 is 12, so the mean would be 6. 6 and 7 is 13, so the mean would be 6.5. Okay. And so those are all the possible sample sizes, all the possible sample means for all the unique samples size 2 from this population. Now, this would work with any size population, any size sample. Obviously, it gets a little hard to put it on a legal pad. And so I'm using the very simplest case that I can think of to demonstrate this. Now, if we looked at these sample means now, we know that, first off, the grand mean for all of these sample means is 5. Do the math if you want to. But the population mean is 5, and so the grand mean of all these sample means is also 5. If we distribute these things, see if I can do this without making it really, really bad. If we distribute these things and we distribute them around 5, we know 5 is the sample mean. And so let's see, we've got what, 2 5s. So we can cross off 2 5s. And we can do 1 5, 2 5s. We've got 2 4.5s. We got 2 4.5s. We have 2 5.5s. We've got 1 6, 1 6.5, 1 4, and 1 3.5. Now, I know it really doesn't begin to look like it quite yet, but this is beginning to take the shape of a normal distribution. And as it turns out, sample means, all possible sample means of any given size from a population is perfectly normally distributed. Now, even if the population isn't normally distributed, even if the population is, the tail is skewed off one way or the other, and it's got a couple of bumps in it, a lump or 2 in it, or whatever, even if the population is not normally distributed, the distribution of sample means of any given size from a population will be normally distributed. And that's the primary reason that we use samples in the modern scientific method, is because samples work, because they are normally distributed irregardless of how biased the distribution might be for the overall population. And so that's why we always prefer to work with samples as opposed to populations, because we can predict how those sample means will look. Now, it's not one normal distribution, it's a different normal distribution for sample size. So the distribution for sample size of 15 is different than the distribution for sample size 50. Not radically different. They're still both normal. It's just that one's a little flatter than the other. Now, once you get to a sample size of, say, a couple of hundred or so, all the distributions began to look very similar. They're never exactly similar, but they all begin to look very similar. And we know what the probabilities are. We know what the critical values are for any size sample to be able to say, okay, if something falls outside that range or outside that range, it is a significant difference. All right, let me stop. Questions? I told you this stuff's pretty simple. I mean, they wouldn't let me teach if it wasn't. All right. I'm going to do one quick little addition here, and then I'm going to pull the plug on this video. And in the next day or so, I'll be producing two more that'll be more about specific t-tests. Now, you do have examples in the next block of resources on your on the Azure Learn site. And they're examples of the different t-tests. I just want to kind of in a general sense, a generic sense, talk about the different comparisons that are available within the t-test. Now, first off, why do we call them t-tests? This is, it can be a long story, but I'll make it real short. There was a man by the name of Carl Pearson, who was a noted Swiss, Swiss, German, French. I mean, he kind of was a mixture of different nationalities in the area there, but he worked primarily in Switzerland in the early part of the, or last part of the 19th century, very early part of the 20th century. And he taught psychology. And in the end of the 19th century, early part of the 20th century, psychology was the, you know, the rising star among disciplines. And it was, everybody wanted to be a psychologist or a psychiatrist. You know, Sigmund Freud had kind of, you know, everybody was convinced this guy was a genius, even though we know he probably wasn't. But he had some, you know, he had some thoughts about human behavior that were unique. And everybody wanted to be a psychiatrist or psychologist. And so that was a very important doctoral program to prepare people, you know, to be psychologists or psychiatrists. And so Carl Pearson, one of the things he taught was research methods, research methodology. And he was teaching the modern scientific method, and he came up against this idea, this notion of, you know, when is a difference a difference? When do we know this is different from random chance? And that led to some of the early developments in statistics. Well, he wrote up in a long syllabus for his class these three tests, these three ways of looking at differences that we're going to talk about in just a minute. And other professors saw that, and they wanted to, you know, thought he ought to publish it. You know, he should put it in a journal so that, you know, he would have the copyright to it, but at the same time, so that other people could use it, because these things really seem to work and they seem to have a lot of validity. And so he published in a mathematical journal called Biomathematica. Yeah, Biomathematica, I think. And it was published under the author's name of student's teacher, because he didn't want to publish under Carl Pearson, because he didn't want to be known as a mathematician. He wanted to be known as a psychologist or a psychiatrist. And so he didn't want to be known by one of those, what were considered to be vocational sort of subject areas at the time. And so he published it under student's teacher. It then became to be known, as they shortened that, as the student's t-test, T from teacher, and then the student went away, and now it's just referred to as t-test or t-distributions, distributions of sample means. It works up to 2 sampled, up to 2 means, doesn't work beyond 2 means. But that's all they were trying to do back then, to find a difference between a control group and an experimental group. And so the t-test, as it turned out, Carl Pearson was much better a statistician and mathematician than psychologist, and most of his published work ended up being on research methods and statistics, and not much he published really made it very far in the areas of psychology or psychiatry. And so by the time he had began publishing other articles about statistics, he had decided to go ahead and, you know, allow himself to be the author of it and be known as the author. Now, he did a lot of these early statistical methods we're going to talk about were Carl Pearson's inventions. And the t-test is the first of those. All right, let me get tired of drawing this thing. Maybe I'll just have papers printed with normal distributions on them. Now, there are 3 primary t-tests. Now, remember that t-test, t-distributions are distributions of means, mostly sample means, but there are some different means in here. So t-distributions are distributions of means. Now there are 3 questions related to means that we can use t-test for. And the first question is, is called, does a particular sample differ from the population mean? Oh, okay. Forget about all the typos, all about misspellings in there. I'm sure I will make some as I go along. I'm not a good speller. Okay. First guy down in spelling bee, always. They thought I was being lazy. I just couldn't spell. And does a particular sample differ from a population? And that particular statistic, which will look familiar, is the sample mean minus the population mean, and that's the big M, the big mu. And on the bottom is something called SEM, which, similar to standard deviation, is called standard error of the mean. And so it's calculated very similar to standard deviation, and just looking at just using sample means. And so this becomes what's called a one sample t-test. But what you're actually doing for a one sample t, you're saying, okay, these are units of what's called standard error of the measurement. if this is the population mean here in the center, and a sample mean is, say, in here, now there is a little leeway here, okay? These differences are not exactly on 2 standard errors of measurement, depending upon sample size. So let's say for a particular sample size, let's say, I don't know, n is equal to 20 sample size. Let's say the critical values for that sample size are right here. That's a critical value, and right here, that's a critical value. So if a sample mean from this formula, whatever, we have to know a couple of things here. One, we have to have the sample data, and two, we have to know what the population mean is. I mean, we can't calculate the population mean. We have to kind of know what it is. You know, what's the average height in a building? What's the average IQ score in a school? What's the average blood pressure in a unit? I mean, we have to know what the population average is. And if say a one sample t value is in here, then we say not significant. One sample t value out here, we would say significant. Now we express significance in a numeric quantity. And it's generally called an alpha, for lack of a better term, but you'll see it in the, once we start looking at actual output, we'll talk more about that. But you know, the alpha is typically 5%, a 95% chance of it be random error versus 5% of it not being random error. And what we use the statistics for is to calculate the probability of it being random error or not. So any what's called significant value or p-value, probability value, less than 5%, we consider to be significant. And that's generally what's reported on most statistics. Now, let's say we ask the second question. Now, we're looking at 2 sample means. And so that formula, which is called an independent t-test, is mean of, say, the experimental group minus the mean of the control group divided by standard error of the mean. And once again, it's figured a very similar way than reading. So experimental group minus control group divided by standard error of the mean. And so in that regard, this midpoint here becomes 0 different. And the critical values then become, at what point is it 95% different? In other words, if there's a range in here of potential differences, and 95% of them would be within that range. And so if the difference between those two means is not within that range, then it's a significant difference. Now, once again, I'm looking at two-tailed things here. I'm not talking about the one-tailed example. That just drives you nuts if you try to think of it all at once. It's called an independent T. And we'll look at a lot more, you know, in the next video or two that I put up, because I'll go through each one of those separately and looking at data to talk about it. And then finally, the third question we can ask about group means with t-test. I guess I need something else. Do subjects change from pre-test to post-test? And so you only have one group, but you pre-tested them, so you have a score at the pre-test. You've post-tested them, so you have a score at the post-test, and you want to know, did they improve from pre-test to post-test? And that particular T, which is called a paired t-test, is pre minus post means, pre-mean minus post-mean, divided by what's called standard error of difference. And once again, it's a distribution of all possible differences between pre and post. Now, this was basically what stats looked like for 10 or 15 years. But it was limited to only being able to look at most two group means. And as scientific method evolved, people wanted to look at more than two group means. They wanted to look at multiple group means. And so there needed to evolve a new way of doing that, and we'll deal with that in the next section. But this section will be, we'll kind of limit to the t-test stuff. Questions? Now I'm going to do an example with a short video for each one of these t-tests. So, you know, that won't take too long, but I just have not had the opportunity to do that yet. Any questions? Deborah, are you trying to ask? Yeah, you need to.
I'm sorry, I forgot to unmute myself. I apologize.
Right.
It's been a long day. Will we be having different examples that we can keep practicing this to see if we really understand it, or will it just be the few that you present in your video?
No, you'll have different data sets that we'll use in video, but the data sets will begin to get large enough that you can look at different variables within them.
Okay.
Yeah. And so you will be able to practice, and I'll offer some, I'll offer some suggestions there. I'll offer some questions that, take a look at this question, see if you can answer this question, see if you can answer this question. And then we'll kind of work through answers for all that. And, when, as we start getting into the assessment pieces, remember, this is all mastery learning. These are all formative. None of these are the grade that'll kill you. I mean, these are all formative experiences in which I'm going to try to provide you with enough answers to, kind of make some sense out of it. questions? Others? All right. Well, then I'm going to stop this share. I will put these pieces under a folder next to the video when I put the video up, which might take a little while because you know, YouTube and Zoom have been running a little bit slow in processing videos, so it may be tomorrow morning. I don't know if I'll get them up this evening or not. They're just kind of not being very cooperative right at the moment, and may have something to do with load. I think Zoom go from 10 million customers to 260 million customers literally overnight, and I imagine YouTube did about probably not quite as bad, but I imagine, you know, I think YouTube bumped up like 30% or something literally overnight. So you know, a lot of people are discovering these platforms, and us that have been using them for a while are paying the penalty for that. But we'll see. You have to be careful with Zoom, though. You know, Zoom's built in China, by the way, and so you know, I'm not a Chinese agent, and I don't, you know, I'm not trying to be, you know, one of those bots or anything like that. But you know, Zoom is built in China, so you got to be careful. All right, I'm going to cut off this recording.